Hey, this is Dr. B here, and let's talk about measuring energy. Now, there is no simple device that you can just stick into something and have it spit out energy units. What scientists typically do is they have things undergo a temperature change. From that temperature change, they determine an energy change. And this can be used to figure out the specific heat of a substance. And if it's an unknown substance, you can use it to identify unknown substances with very cheap equipment. We can also figure out, using things like this, how much energy it takes to heat a certain amount of water or any substance. And we'll use this, in this case, to figure out how much energy it takes to make a cup of tea. So let's begin. Imagine you have a liter of water and you want to change it by 1 degree Celsius. That's a pretty standard thing to do. Just ask Mr. Science.
In the metric system of units, the amount of heat required to raise the temperature of 1 gram of pure water by 1 degree Celsius is defined as a calorie.
Thank you, Mr. Science. I don't like using the calorie because that's this unit here and it has the little c, and students are always confusing it with the big C, which is nutritional calories, which, by the way, is far more familiar to people. But let's take a look at all of them. For that 1 degree of temperature change, we're talking about 4,184 joules, but only 1,000 scientific calories. I hope you're seeing that a joule is a tiny increment of energy. And as we get bigger, we can go to British thermal units, and it's only 4 for that 1 degree of temperature change. For nutritional calories, it's exactly 1. I don't know why that doesn't show up there, but imagine a 1 right there for nutritional calories. And fine, so those are some comfortable energy units. Let's apply it to a pint of Ben & Jerry's ice cream. Imagine you are going to consume that entire pint, I wonder if you have, and let's figure out how many joules or kilowatt hours of energy is involved. It's over 4 million joules. It is about 1 million calories of the scientific variety, about 4,000 BTUs, about 1,000 nutritional calories. That's a lot. But it's only 1.16 kilowatt hours. So those are some conversions from one form of energy, one unit of energy, to another. We can apply these temperature changes that we were referring to by talking about specific heat. I think of it as substances that are easy to heat per gram or difficult to heat per gram. I say per gram because the most common form here is the specific heat formula, which is involves Q, which is heat, M, which is the mass of your substance, not its volume, its mass. C is its specific heat. Water checks in at one of the very highest of all known substances. It is very difficult to change the temperature of water compared to other substances. It requires more energy per gram for each degree Celsius. And the units give it away, right? Joules per gram degrees Celsius. How many joules of energy it takes to change 1 gram of that substance by 1 degree. And delta T is your temperature change, so we can apply it to things. Let's do that. Over here we see some metals of certain masses. They tell you how much heat was absorbed when they changed their temperature and how much the temperature went up by. All we have to do is plug this in and solve for C. Looking at this formula, I hope you would agree that C equals Q over M delta T. And that's all you need to do. We can then compare it to a list of known specific heats, and here's one right here. Notice, as I said, water is pretty much at the very top of the list. That's a lot of energy to change the temperature of water. It goes down if water's in a different phase, and most of the metals are significantly lower. Okay, if you plug this in, you'll find that the first one is strontium, the second one is barium, and the third one is magnesium. So plugging in those numbers, for example, would give you a value of 1.023 for this situation, meaning you're dealing with magnesium. I hope you can appreciate the power of this. So you have some unknown substance, and you can figure out its specific heat. It doesn't even have to be pure. You won't have a table for it, but if, say, you had some rocks on a beach and you calculated their specific heat, well, that would be it for that rock. Okay, final calculation. Let's find out how many joules of heat are needed to make a cup of tea. So notice it's a cup of water. We're going up from room temperature to boiling. Since this is milliliters and we're talking about water, since water has a density of 1 gram per mil, it is 237 grams. And this looks like direct plug-in to me, right? We're solving for Q, joules of heat. There's our mass. There's our, we don't have our specific heat, do we? We got to look it up. Here it is, water, liquid water, 4.184 joules per gram degree Celsius. And delta T is hiding in here. If we're going from 25 to 100, that would be 75. So plug it in and let's find out. There you go. Take a look at the units at least this one time to convince yourself it's spitting out energy. Grams divided by grams equals 1. That's gone. Let's see. Degrees Celsius on the bottom, degrees Celsius on the top. That cancels. The only unit left is right there, our joules. And it's 74,000 joules, or 74 kilojoules. We could convert this into any of these units that we want to. And that's how much energy it takes to make a cup of tea. This is measuring energy.